let's talk about infrared spectroscopy here. So let's just start right off by talking about sources and ways that you can detect it. So for sources, we have a silicon carbide glow bar, or you could use a laser, but the glow bar it gives a lot of different wavelengths. It gives a lot of different wavelengths all at the same time, so that's probably better and much more common. So then as a detector, you need something that's going to create a voltage or a current as a result of interacting with heat, which is basically what I think of when I think of infrared light or electromagnetic radiation, I guess is what I was trying to think of. So you could use something like a thermocouple or a pyroelectric detector, which changes polarization as a result of heat. You can use something that changes conductivity as a function of heat, or a photovoltaic. So the trick with IR spectroscopy, what makes it different from UV vis, is that we don't actually have a great way of like monochromators don't work that well for heat. Like you can blow a hairdryer in a monochromator all day and you're not going to get a single wavelength out. So we have to do something really tricky, and we'll use something called an interferometer, which was invented by Michelson in 1880. So this is an interferometer. So let's talk about how it works. You have this source, like a glow bar source, that gives off radiation this way. Then you use a beam splitter, and half of the beam goes up to this stationary mirror. So this is half of the incoming radiation from the source. Half of it goes to a stationary mirror, bounces off, and comes back through the beam splitter to the sample. The other half goes over here to the moving mirror and then comes back. And so because there's a difference in the path length that's traveled by these two little bits of light, they're going to arrive a little bit out of sync. So when they were coming from the source, they were in sync, and now they're like a little bit off of sync. And this is for all of the different wavelengths, because you have a lot of different wavelengths coming from this source. So you have a little bit off sync. So you have some constructive or destructive interference when you bring them back together, because they're both going to go to either one of the mirrors and then come back together and go interact with the sample. So both of these interact with the sample, and then they're detected all at the same time. So it's a sort of a complicated idea to wrap your mind around. But you know, the one thing that makes this work is that you have to know precisely the location of the moving mirror at all times, and how that relates to the difference in path length between the light that's going to and from the stationary mirror and the light that's going to and from the moving mirror. So you use a laser so that you can precisely measure where the moving mirror is at all times, and that is what you need in order to deconvolute the detector spectrum. So essentially, you have the simultaneous interaction of simultaneous detection of all of the different wavelengths that you have from the source. Only they're a little bit off kilter when they get to the sample and interact with the sample because of the difference between the moving and stationary mirrors. So what you end up getting is an interferogram, and it looks like this, where you have detector voltage here, and this is essentially the source spectrum minus the sample spectrum. So then what you need to do is to do some relatively fancy math to break it down into each of its relative wavelength components, and then you need the information from the position of the moving mirror at each time for each wave, and that tells you the difference of the path lengths for each wavelength that was interacting with the sample. So then you do a Fourier transform, and you know it's some fancy math. You don't need to know what it is, but it basically deconvolutes a whole bunch of deconvolutes a spectrum into its component sine waves, which are basically the wavelengths. So then you end up with a spectrum that looks sort of like this. This is a really bad representation of an IR spectrum, but basically a percent transmission on the y-axis, and on the x-axis you have the wave number. And a typical IR experiment goes from 400 inverse centimeters to 4,000 inverse centimeters, because that's where you have good brightness from the source, as well as sensitive detection from the detector. And, okay, right, one more thing. The last thing I wanted to talk about is that water absorbs in the IR, so you can't just, like a UV vis, you can't just use water or glass or the normal things that you've been using in the UV vis in order to get an IR spectra, because the sample containers would produce a large signal. So there's a couple of different ways that you can do it. You can disperse it. You can disperse your sample in mineral oil, if that works, or you can press like 1% of your your sample into mix it up with KBR and then press it into a pellet, and you would use like 1% sample-ish to do this. You guys are going to learn a lot about this in organic, but this is sort of just to give you an idea of what's going on underneath the hood of an IR instrument.